Hello there! I wanted to make another video about what I have been up to in the upscaling topic, hobby topic. First I wanted to share real quick my thoughts about Magnific.ai. It has been a lot of talk about it in the last 3 months, I believe, or 3 months ago. This is an image upscaler and enhancer, they say, on the website, and the very first example you get, this is the input and the output, and it is a nice image. My thoughts about this and the problems I have with this is, if you look at the leaves, there are suddenly holes in it. The structure looks completely different. So for me, this is a different image. I'll call it a non-faithful upscale. It could be a different plant species. And I like how the diffusion paper called this. They said that they're carefully avoiding the term super resolution, and they say this process is more akin to image generation based on a real image. I think it's the same case here for Magnific.ai, or could be a problem with any of the diffusion-based upscalers. That this is more of an image-to-image detailer and enlarger, so to say. And I just wanted to show another alternative, because Magnific can be quite costly to run. This is somebody made this chain for Comfyui. You can see the link here, and there are different versions, version 1 to 2.2, but this is something that you can try out for free on your local machine. I took this image from the Magnific.ai examples again, and this is how my output looks like. This was with version 1. And I used the analog madness checkpoint for it and my Nomos 8K SCHL model for it. I can also show it here. I was trying around a little bit, so you can see for this I used the cyber realistic checkpoint, but then also the photo checkpoint. And so you can go in there and see that they're a little bit different. But I like what it does with the hair. If I show this example, how this white, pixelated mess gets turned into hair. I like that. But we always need to be careful, of how much it changes the actual input to be a faithful upscale. But, this only depends on your use case. If that's actually what you want. If you want the image to be changed and, just look as good as possible, and it doesn't need to be the same image, then this is completely fine. I'll show another try. This is with version 2, but you can see the denoise settings were increased, so the output will be more denoise, leaves more creativity, so to say, but the image will be different. So we can change the denoise a little bit, so turn it down to 0.3 a bit, and then it looks closer to the input. So you can, experiment around with it and try it out. Then other networks, there's constantly new research and constantly new networks. Those are some of the pages you can watch out for, but it just feels to me like there's constantly new stuff coming out and to try out. One of those lately was SPAN, Swift Parameter Free Attention Network. You see, we as a community already trained 22 models and published, we train way more than we publish, but we published 22 models with this network. It's a very fast one. There's another one I'm currently testing out and training models for. That's also pretty new. It reminds me a little bit of dual aggregation transformer too. That's one of my favorites. Also SR former and het L. Those are some of the bigger transformers, but they are my favorite networks, for upscaling models. There's also adaptive token dictionary that I'm currently watching out for code release, that is, that might be interesting. Then on the diffusion based side more, we have also, content consistent super resolution, which tried to solve the problem a little bit more, what I was saying about the fidelity, so to say, like how closely they still match the input and don't, change it too much. And there's also CCSR. You can try those two out. I also have an example here of input, CCSR and CSR, how they look like. You can also go and have a look at it. There was also diffbir that you can still test out, still go and try out, which I liked when I tried it out. And there were some that I didn't really like that much, like rest shift stable SR, post. And yeah, there was just, too many settings to fiddle around to actually get an output that I want. There's also SUPIR, the newest talk. Right now they also have a website. You can see, I just, put the car brand or logo or what this is next to each other to show again that it changes the input. Like if you upscale a car, it might be, suddenly a different brand of car. But again, if that's what you're going for, if you don't mind the input being changed, then that's fine, or being changed too much in that sense. The thing here is SUPIR has a high requirements. So you can see 60 gigabytes of RAM and 30 gigabytes of VRAM. That's, I don't have a graphic card like that or a system like that at home. But they also put in settings that you can use, like heft precision and tiled, so that it takes less, with 12 gigabytes of VRAM. So this could be run with RTX 3060. I didn't try it out, but like this, it should be able to be run on an RTX 3060. And in the community currently, or on the Enhance Discord, they're currently testing and trying it out. But I wanted to show, and I think a lot of people also here are waiting for an official online demo release. But this can, of course, be tried on and run locally, or also on RunPod or any other GPU service. Then concerning Chainer, I just wanted to simply show that they made a package called Spandrel. So they took the super resolution part out of Chainer and made it its own kind of independent package. Their hope basically was that more people this way, can use that module, but can also, as a Python package, but can also, contribute and, for example, add support for some of the networks that I just showed, for example. You can also see all the model architectures or networks that are supported with Spandrel. So it's quite a lot. So you can, use Chainer or this Spandrel packet and use any of the models trained for any of these networks. So that's a lot to try out and to just experiment with. Then neosr, I hadn't showed. The last video I made was still with, RealWebPhoto training base, or was it Redux? But neosr is a new training software that Mussel made that we have been using in the community for a while now, or lately have been using. And the great thing about this here, there's also instructions, and there is a whole wiki section about it where we have a configuration walkthrough, so you can look at all these options. If you had been confused about all these options in the training option files from my last videos, you can go and look at every single option in here and what the default would be or what it would be doing. So you can have a look at the configuration wiki of neosr. And here is all the supported architectures of neosr currently. We don't just, throw everything into neosr there is, but some that we are interested, we add it. You can see it also here under testing, for example. We add new networks, then we try it out as a community, and if we think it, doesn't really add value to what we already have and what's established, then we throw it out. We had some of those like edat and bicubic++ and stuff. We all tested them and threw them out again. And some of them, stay here that we like. Now, some of those networks are, way faster than others, and some of those are more lightweight, but they're also might be less capable in what they can handle concerning, how many degradations you want the model to be able to handle, or you train it and with what strength. Just to give an overview, I, did a test. So I took 50 images, you can see it here, 265 by 265 pixels, and then I just upscaled them with each network option multiple times, at least 3 times, and took the fastest run time from the fastest run. And then, I listed it up here for you, sorted from the first is the fastest one, on my system at least here, with neosr test script. That was compact, and then, the slowest one would be hot-L. But, so you can see the big difference on how fast they are in upscaling those 50 images comparing to the slowest option. But there's also in general a trade-off, like the slower ones in most cases are able to handle degradations better and give a better output. So it depends on your use case. Do you want to train a fast upscaling model, and how many and with what strength degradations do you have in there that the model needs to be able to handle, and so forth. Now, just to get a small impression, something you can do is you can simply take the officially trained models. So most of them train on bicubic with like diff2k or something, some standard data set, and then they release a public pre-train on their GitHub repo or where they posted their code. And so you can take, just to get an idea, you can take that pre-train and then upscale the same model with all of those different pre-trains, and then, go and compare them and have a look at them. And this gives you at least an impression on how the model performs if it's trained on bicubic only. It isn't a whole picture. It won't really tell you how good the network can handle multiple different strong degradation and stuff, but it can at least give you an impression on how the model can perform. A project I wanted to show, the Evangelion episode 16 community upscale. You can see, or what happened is Comfyui released his dataset he has been working on for multiple years. And, he said here, he released a paired dataset, and his goal, he said, is to create an upscaling model that basically makes this episode look better than the Blu-ray release there is, because there is details, for example, missing in the shadows in the Blu-ray release. So then there was a call for model trainers to train models on this. This started, picked up activity, just to show here. They talked about warping in the dataset and so forth. So they released an overworked dataset then. And then we trained multiple models, or different people trained multiple upscaling models, which we then all, put together some validation images to compare all of those models. I can also show here, you can take one of those comparisons, and then, you can click through those to compare them, or take another one and then compare them. You can also go to the slider comparison, and then, take the input and one of the trained models, and then compare them to each other. So that is what we did. We made multiple models on this dataset, and then we used this model to upscale a short test sequence, and then TPT was able to add stabilization or temporal coherence. It's something I want to show here real quick. Since we are training single image super resolution networks, they do not have temporal coherence. So they just take each frame and upscale each frame separately, which will lead to, kind of flickering. I wanted to watch the letters on that crate box on the right, especially that C, and then look how it flickers or changes around. And now TPT was able to, stabilize this and add temporal coherence, so it looks way better. Then TPT was also experimenting around with color fixes, because as you can see, for example, my dot model changed the color. There was a color shift in there. As you can see on the left side and on the right side, we played around with different color fixing methods, and the wavelet color fix was pretty good, which comes basically from the SDWebUI StableSR repo, which was made there, the script, and then also got used in, for example, diffbeer or some other diffusion-based upscalers that applied this wavelet color fix to. And I made a project page on the Discord about it. So if you want to keep up with the development of this specific project, you can go and have a look there. Now some of you maybe know my website where I upscaled a lot of images or upscaled images with 300 different upscaling models I was gathering together at the time before starting and trying to train my own models. And now this page has become, it's 70 gigabytes on the GitHub repo, so it became difficult for me to update. And I, now made a different page because I myself am at 113 outputs just with all my self-trained models. And so I made this site currently for my self-trained models. The others are still, work in process, where I, host the images externally now, so this shouldn't blow up as much on GitHub, in file size, I mean. And then you can see I have 113 outputs for an input, which can be seen here, but I visually went through all of the outputs and made a filtered result section of outputs or models I think performed well on that input. And for each input, you can see that I wrote its purpose. So this is a photo examples. We are looking here for detail preserving models that are faithful, that preserve the depth of field and preserve details. And then I wrote which one of my self-trained models I liked on those and ordered them at the top before then, being alphabetically ordered from here on. So you can see here, we can, go here and look at this tail light, and this is what I wanted to show. You can see the tail light is still diffused, so this doesn't de-blur, it preserves depth of field, and also, there is still the scratches, it preserves details pretty good here on this input or the text. To show a bad example, we need to go to the unfiltered result because I took it out, of course. But if I take the most extreme one here, you can see what it does, for example, for this tail light. So it de-blurs, sharpens it very, very strongly. So that's not what we wanted. We wanted to, for this input at least, we wanted to preserve depth of field or bokeh effect. And then, I have some more examples. You can go and check it out. Then I made a I make a Google Drive folder with all my models in there under releases, also my datasets I put in there. And on OpenModelDB, Kim added a lot of my models, so I'm grateful for that. So I have 37 released models on there now. And I just wanted to show the experiments I had done so far. So one of them was, the Flickr high quality faces dataset. I trained 2 models with it, and then I made a curated version of this called FaceUp and trained models for it. This should be familiar from my last YouTube video because how I made this is what I showed there. Then I did the same thing with the LSDIR dataset, making an SSDIR dataset. So just a curated dataset out of this and trained 2 models on it and released the dataset too, of course. And then I made a multi-JPG series, and the whole goal here was that it is non-deblurring, non-sharpening, so meaning it preserves depth of field, and trained some models for it. The Nomos Uni dataset is a general purpose one, so these are, trained on photo and anime and drawings and, different things meant for just to be a, multi-purpose model. There is one FHA2K in here, which is an anime model, but just, also non-deblurring, so depth of field preserving. Then I made an exposure correction series on compact. The experiment on here was, can I make a compact model that, corrects overexposed images or underexposed images? And the interesting thing here was they were trained with no brightness loss, so none of the losses was focusing on brightness, but just the normal losses, the gain loss and color loss were able to make this work. So that was a funny experiment. Then I made different anime models. This one I already explained, therefore field preserving. Then I made anime models that were, on the fly degraded, trained with the RealESR GAN pipeline. Also different network model options or options thereof. Then I made LUT-VAE models. Those were trained on Musel's LUT-VAE dataset FHA2K, which simply means that they were realistically degraded and should be able to handle those degradations. Then I made anime models with just specifically H.264 compression in mind. Then I made an anime model that was trained with on-the-fly degradation. So in addition to all the degradations that we have in the RealESR GAN pipeline, this additionally has on-the-fly video compression degradation. And you can see here that it's, not just H.264, but also 265 and MPEG, and, with ranges and CRF range and bitrate range. And so, yeah. So this was this experiment with the vide SeeSR data code on the GitHub repo. Then I made 3 Evangelion pair-trained models. And then I made lexica models. These were meant, so I took, I took AI-generated output, made a dataset out of it, and trained those to specifically work on AI-generated images. On the right, you can see that there was a compact, prototype models where I just, I added some blur to the dataset, then some more blur to the dataset, then JPEG quality 80 to the dataset, then, only box downscale, and just tested all of them to see what would be the difference if somebody were to just add, a little bit of sharpening to the HRs or a little bit of, blur to the LRs and so forth to train my models. And then on SD Next, they added trainer, so all my models could be used there. So I made, comparisons for there on AI-generated input, basically. Then I made photo models. These were some of my first ones. You can see the SSDIR models, compact models also, where I trained, a compact model, but then I trained one without degradation handling. Then I played one with only JPEG compression added. Then I trained one with the full ESR GAN pipeline added. And then I made interpolations of those. And so this was at the beginning when I first started with training models. And you can see I, made testing datasets. I, inferred them. Then I used matrix, so LPIPs, to compare all of them together, and then I started playing around with interpolations. And this actually worked way better than I thought. So what I did is, I trained a model with no degradations or only JPEG compression. And then I trained a model, LSDIR plus R, which is way too strong. The R versions of these series were way too strong, way too much degradation added. But then I would interpolate those models. So I would, 70% the non-degraded, and then 30% the very strongly degraded. And then I would get a model that could handle, degradations to some point, but would have better output than the one that was fully degraded. And then, I did the same thing again with 50-50, so 50% each. And so this was actually an interesting way of creating more models out of 2 trained models, where you would, decide of how much degradation can this model handle with the interpolation values. And this worked way better than I thought, and it was a pretty interesting experiment. And then I trained, models with JPEG compression only, but with the RealESR GAN pipeline. So the blur kernels were still in there, but for example, the noise had turned down to value 0. And I was playing at first around with Nomos 8K-S, which simply meant the safe for work version of that dataset. And then I made this, and then the C was a compression added. And then I asked in the Discord, and some of them liked the preferred the compression edit, which led me then to, create all those other models, the SC hot L model, the SR Farmer model, and the hot S model of this safer work compression edit version of the dataset. Nomosek is a photo dataset. I need to add LSTIR2. And then I played around more with the RealESR again, strengths again, values, because on the top right you can see, the default config that has been used in RealESR again, and that I from then on seen in all the code repos. So like from Hot, when they released Hot, they used this one to make the real models and so forth. And the only problem I had with this here is it's very strong values. So this is randomized, of course, but just to show the worst case or the most degraded, version, it is when it would, put noise 30 to an image, then JPEG compression 30, then again noise 25 to that same image, and then JPEG compression 30, and that's not even all the degradations that are in here, but I made a little, on the bottom right, a little example of how this could look like. Now the values here won't translate directly to the values in the noise added through Chainer, I believe, or I would assume, but still I wanted to show what it could look like, and I don't believe that anyone would try to upscale a such horribly degraded image. So I was playing around with degrading, playing around with lowering those values, at least the most extreme values, so the highest values. And then this is what I made out of it, like all those span OTF weak, strong, medium, and compact OTF weak, medium, and strong model versions out of it. As you can see here again, where I was playing around with it. And then the 1x, 2x models that you can see on the top right from my Google Drive folder was simply I would take the dataset and then upscale it with, for example, the OTF medium model, and then get all these upscaled versions that are not the same size as the ground truth images. And then I would train a 1x model, so a model that wouldn't resize, on the input of the so the output of my upscaling model and how the images should look like. And the goal here was to eliminate artifacts that are created by the upscaling model itself. So that's also a strategy you can try out when training models. Then when I was testing my models, for example, on this input, what I noticed is that the models trained with the RealESR again pipeline performed the best, but at the same time, the Ludwig models that were trained on anime input also did not bad on this input, and which was a little bit surprising for me because they were trained for anime, so no real photos were in that training dataset, but degradation handling must be good. So I was looking at that. This is where the dataset came from, and how Mussel used Ludwig to generate those images. So, he suggested that I simply train my own Ludwig degradation model, which I then did. I went to the code base, and then I remembered that SeeSR on their repo released Real LR200, which includes 200 real-world low-resolution images. So I simply took those and trained a Ludwig degradation model on it for 2 nights, so for 17 hours. And as you can see here, my degradation model, the left is the input and right is the output, and you can see how it added realistic noise. I really like the noise that it added here to that input. And so I had a game plan to make a new paired dataset for, realistic photo upscaling. And what I tried to model here was, the case of somebody taking a noisy and blurry photo and, putting it on Instagram or whatever, where the web service scales and compresses the image. And then another image user would see that image, would download it and re-upload it somewhere. It could also be somewhere else on the web, where the web provider again scales and compresses the image, and then finally somebody downloads that image and wants to upscale that image. So we need to handle, blur, noise, compression, recompression, scaling, and rescaling. And so at first I took a realistic blur dataset and degraded it, but the results weren't too promising because the motion blur was quite strong in here. So I took I found a blur generating code, which you can see. I tested it out on this image, so you can see lens blur, so realistic blur applied to all those images with different strengths. And based on the impressions I got, I chose a strength that I wanted to apply to my own dataset. And then you can see I took the Nomos 8K dataset. Those are, the images in there. And then I applied lens blur to that dataset, so you can see it here, how it changed. Then I applied noise. So you can see on the top right image how there is a little bit of noise now in this image. Those were all, applied with a random probabilistic value. So some of them could be stronger, or the left bottom image looks pretty much, almost unchanged. And then I applied scale and JPEG compression, and then I again reapplied scale and JPEG compression, and you can see now how the final, training images look like quality-wise. Then I trained the model with it, and you can see I used RGT for this, but this is how it looked like at 60,000 iterations. And then I realized, or I experimented around, and I could see this when we increased the ground truth size, the crop size during training, it was way better able to handle that lens blur. And then I increased it again. And you can see, if you go to that link, you can see the results now at 260,000 iterations. So after 109 hours of training on my PC. And then I tested it also on some realistic images on the LR200, real LR200 dataset itself. Thoughts I had about this is that I need to tune down the lens blur. It seems to be difficult to handle lens blur. And I had it a little bit too strong, I think, from looking at those. And then I want to play around with my other degradations still to get better results and be able to train a better model. Something else I looked at was degrader. You can see this tries to apply realistic image degradation, so we could make another dataset. I actually made a dataset out of it again on the Nomos 8K, so the same one I used for here. But I disabled the mosaic step in here because just the dependency setup was a little bit more complicated for that. So I left the step out, but it still applied blur, noise, CFA, and JPEG. And, I just used compact to do a prototype real quick because it's fast, so I can prototype with it fast. But degrader seems to have degraded the LRs a little bit more than how I had it, and you can see the noise added there. That was my biggest point I've seen. I think the noise added wasn't really realistic in my opinion compared to my own degradation model, Ludwig, that I had trained. But I can combine these approaches, or take specific degradation steps and use it. So yeah, what I'm trying here is still playing around. I'm still experimenting around to get a good realistic model with good realistic pair dataset. And yeah, that was my video. I simply wanted to show, the updates and all the experiments I basically did so far in this, upscaling subject or topic. And I hope it was interesting and insightful, and thank you for watching.